Good morning, guys. Hey, this is John Michael Hans from Intel, and I'm the SNIA SSD SIG co-chair. So that we have a SSD SIG as part of the Compute Memory and Storage initiative, which basically talks about all things SSDs. One of the hot topics of SSDs lately has been EDSFF, the Enterprise and Data Center SSD form factor. So I'm joined today with a large group of industry experts on the topic. Many of us know each other pretty well from working in the storage industry together, and a lot of us were actually together at the OCP storage meetup last year. And unfortunately, we had planned a pretty cool meetup and panel at the Open Compute Global Summit, and as many of you guys know, that was canceled due to COVID, so we didn't really actually have the live panel and got to showcase some of the EDSFF stuff. So today we're trying to kind of recreate some of that magic by having many different companies go over their views on the EDSFF form factor, how it impacts their companies, their data center businesses, their product families. And so today with us we have Paul Kaler, who's a storage architect in HPE ProLiant servers. We have Bill Lin, who's a server advanced engineering architect at Dell. We have Jason Adrian joining us from Microsoft Azure, who's a storage hardware architect, and now also chairs the OCP storage workgroup. We have Ross Stemford of Facebook, who is a storage hardware engineer, which doesn't exactly do it justice. Ross is a very storage industry veteran, like everybody on this page. We have Jonathan Hinkle, who's the executive director and distinguished researcher for system architecture at Lenovo. And we have John Geldman, who's the director of SSD industry standards at Kioxia. And of course, you have me, who's going to be moderating the webcast, and I'm a strategic planner at Intel, responsible for our data center NVMe SSDs, and I also co-chair this CMSI SSD Special Interest Group. CMSI, I can sometimes get the acronym correct, but that's recently new name change to kind of showcase all the good stuff that this work group is doing. So the way the webcast is going to work, each of us are going to have a section. I'm going to give a quick overview of EDSFF and just kind of the 5-minute summary for those who are new to it. We've done a form factors page on SNIA that kind of has a good introduction to the EDSFF form factor that you guys can go view, and that's one of the ones that can be easily searchable by Google. And we also have my presentation at the OCP Virtual Summit is now up on the SNIA page, which is kind of a basic overview of EDSFF. But this will be a really good overview today, and we'll have a lot of broad perspectives and viewpoints on the new EDSFF form factor. So without further ado, we're going to hop into it. And so what are we at today? And today we have basically in the data center today, the form factors that are used on PCI Express SSDs are the add-in card. That's the card electromechanical spec from PCI SIG. We have M.2s, which came from consumer laptops and mobile devices, which were originally developed for small and light systems. And then we have the venerable 2.5-inch form factor, which of course many of you guys know, kind of derived from the hard drive form factor that fits in a standard chassis in a server. So add-in cards, they are good because they have general compatibility, and that's why PCI SIG has a very robust compatibility program to make sure that cards and systems are interoperable. But bad, it's very hard to scale the number of PCIe devices in a system with the add-in card form factor. One is that if you want to get higher bandwidth, the add-in card form factor does support by 4, by 8, or by 16 host connection, but most standard SSD controllers are only 4 lanes, so it's pretty tricky to be able to scale many number of drives, like say 24 drives in a system is really tricky. M.2s are small and modular, and that was part of the goodness of why they took over mobile devices and desktops, is because they're small. But as you'll see here in the talk today, as the flash industry kind of moves in hyperscale from 1 and 2 terabytes to 4 terabytes, there's going to be a brick wall where it's very hard to scale the performance and power of M.2 devices past a certain point, just due to the physics of the small size of the form factor and the way it was designed. It was designed for mobile systems, so the use with 110 millimeter in data centers, had some challenges on the capacities and hot plug use. It was not designed to be hot pluggable. And as we're going to talk about a lot today, scaling the power past 8 watts and the thermal scalability of using custom heat sinks was very challenging, and it limited the data center use. And then, of course, the 2.5-inch form factor, which everybody's familiar with, it's great for hot plug and serviceability, for the chassis, but it's designed to look and mechanically be the exact same dimensions as the hard drive. So that's definitely not optimal for SSDs. As you'll see, there are new cases where we can actually co-develop the SSD form factor with the system for better total solution. Which brings us to what is EDSFF. So it is the Enterprise and Data Center SSD form factor, and it is a family of form factors, as you'll see from the presentations today, which the whole family of form factors share the same connector, the same PCIe pinout, the same interface, and it's a new high-speed connector. And they have different options for different thermals and power and different scalability and different types of systems. You'll see there are EDSFF form factors that are optimized for 1U. You can see the E1.L here it's the long form factor. This is the one optimized for high capacity. The E1.S is optimized for kind of scalability and for mainstream use. And you have the same common high-speed connector that really brings the whole family together. So you have at least some level of interoperability between the form factors. And then besides that, you have with the common connector, you have the ability to have shared test infrastructure and development and the PCIe reuse. Where today the form factors that you saw on the previous page, like add-in card, add-in card U.2 and M.2, do not actually share the same connector. And so the idea of serviceability and hot plug support has been built into EDSFF. So that's just been built into the form factor. The connector natively supports all that, and the pinout natively supports hot plug and serviceability. And then you have these different options for LEDs, carriers, for carrier-less design, where you have the actually integrated enclosure. You have asymmetric and symmetric versions of it, which we'll talk about the different use cases. But it's really meant to be fully customizable, and you can have a hot pluggable form factor that's serviceable on the front of the chassis, without tools. All right, so a little history before we dive into it. So the EDSFF work group was actually formed in 2017. So at one point we had an EDSFF work group, and it was actually formed in 2017 when there was some multiple form factor proposals going around. NVMe devices had been around for about 3 years at this point, right? The first NVMe SSD was shipped in 2014. The first NVMe spec was in 2011. And in Q3 of 2017, Intel launched the Ruler SSD at the Flash Memory Summit. And I was the product manager for the Ruler SSD, which was super cool. I got to talk to a lot of customers about that project. And there was so much excitement around the product. It was like a breath of fresh air to customers saying, like, wow, I can't, you guys really started from first principles thinking about how do we design an SSD from the ground up, for data center use. But they said, that's great, but it needs to be an industry standard. Nobody's going to use it unless it's an industry standard. So Intel contributed the work to the EDSFF work group. And then Q4 of 2017, the EDSFF wasn't meant to be a long-term thing as far as a work group. So the work got handed off to SNIA and the SFF work group, which the good folks of the SFF work group are now the ones actually developing the specs. And that's where the SNIA specs are located at today. If you go to the SNIA SFF website, that's where you can find all the way to specs. So the very 2018, that was when the first launch of TA1006, which is E1.S, TA1007, which is E1.L, and TA1008, which is the E3 form factor. And then you have the common in the signal specification, the 1009, that brings them all together. And then in Q2, that's really when we kind of cleaned up some of the specs. That's to the pin and signal spec, and you have an E1.S 1.1. And then the thing that happened in 2019 was we really refined the E1.S for mainstream use. And as we started to get customers in the industry more familiar with this form factor, this form factor itself started getting refined to where you have these symmetrical and asymmetrical enclosures that can be used. And then towards the end of 2019 is really when EDSFF started to really pick up, where the OSP storage work group kicked off a lot of thermal methodology, a complete form factor overhaul for what is the right form factor for Flash, for the future, as part of the OCP storage work group. And that's where a lot of the E1.S 50 millimeter got added into the specification. And then now we're at today in Q2, Q3 of 2020, where the actual E3 specification is getting updated for actual mainstream use in Gen 5. And Paul and Bill are going to walk you through that today. So this is a high level view of the entire EDSFF family of form factors. You have the E1.S 5.9 millimeter, which is meant to be kind of the lower power device. It's kind of a 12 watt envelope for EDSFF, which allows you to do stuff like kind of have small and modular things like you had with M.2. It definitely solves some of the challenges that M.2 had, right? You have mounting holes for a standard heatsink. You have this option for a heat spreader here on top of the components, but it allows you to actually have a kind of modular and flexible form factor. But really where we're seeing the most interest today is 9.5, 15 millimeter, and 25 millimeter enclosures, where you have these symmetrical and asymmetrical enclosures. And they all use the same common rail, but they're meant for different server use cases, different power envelopes, for different thermal environments. And you'll see, as the speakers talk through today, the various views in this form factor. But really, the intention is that an SSD vendor, produces one product that can have one single PCB, or one product that can scale between these three different heat sink options for different thermal environments and different servers. And the way we think about E1.S is really, again, you have not as many media sites as U.2, but you'll see here in the slide, you can fit quite a few more of them in a standard 1U server. They've really been designed from the ground up to be a 1U optimized. E1, the 1 in E1 stands for 1U. That's really about a 1U optimized form factor of how do you have performance storage and scalable storage in a 1U server. Now the E1.L, you can see you have a really big board, and that real estate on the board is actually going to be able to use for really high capacity SSDs. So E1.L is really optimal for for QLC, for really high capacity SSDs to get the best total cost of ownership. And you'll see when we look at some of the chassis, it definitely provides the density in one 1U storage array versus the rest of the family. And then you have E3. So Bill and Paul are going to talk quite a bit about what's going on in E3, but think about this as kind of your mainstream U.2 replacement for Gen 5 and beyond, and it really brings a bunch of new device types, but really optimized for a 2U design, and you use them horizontally in a 1U. And you have a full family of form factors. You have this thin and thick, and short and long. But I won't spoil Bill and Paul's presentation. They have a lot of awesome information on this today. So, and connector ecosystem. One of the main things about EDSFF was that they all use this common connector, and you have this by 4, by 8, and by 16 connector versions for the different form factors, and they all are fully interoperable. And it's a high-speed connector that's rated at high transfer speeds on PAM4. So it'll be supporting PCIe Gen 5, Gen 6, and beyond. And really, the whole idea is that you have this one high-speed connector and high-volume connector that will have a robust ecosystem around it, so that you can get it to very low cost. And that happened on U.2 and happened on M.2, and this is the path to scale and cost on the EDSFF infrastructure. So these are the specs. SFFTA 1002 is the actual spec for the connector, and then there's some, there's some support, okay, yeah, sorry, there's some questions about the audio quality. So I don't know if you guys want, if you're not presenting, just mute. Some people are hearing background noise. Great. Okay. So that's the ecosystem, and before I hand it over to our first presenter, I'm going to talk about why one of the form factors, just for an example of when you design the SSD in tandem with the server, you can get much better scalability, and you can get a much better solution, right? Where you look at U.2 and a 1U, and you have 10 devices, 10 U.2 15 millimeter devices in a 1U chassis. You have to put them horizontally to fit on a backplane. And then you have a PCIe add-in card that has a switch or a retimer on there most often, and then cables out to this backplane. Where on the E1.S you have this option on the left here that has 32 E1.S 9.5 millimeter devices in a 1U chassis, and then the one on the right is a 24 E1.S 15 millimeters. So this allows you to get 3.2x the number of drives per rack unit, and if you look at a standard by 4 NVMe SSD, that's a whole lot more performance scalability in a 1U chassis. And then the other thing is you're using this orthogonal connector, and it allows for low-cost attach of PCI Express. So you can have PCIe that's being cabled directly from the CPU in a other types of nodes where you have the CPU closer to the connector. You can actually route the PCIe lanes directly from the edge connector to the CPU. It allows for much lower cost and much more scalable attach for NVMe devices with better airflow. And this is, again, when you're looking at a form factor being designed in tandem with the system, you get an overall better solution. We call this co-optimization, and I believe that the other speakers are going to talk a lot more about this. But I'm going to hand it over to Jason, a member who's from the Microsoft Azure team, and he's going to walk you through a Microsoft view of E1.S and E1.L. Thanks, Jason.
All right. Thanks, John Michael. Before we talk about the new flash form factors, though, let's quickly recap how we got here. For 2 decades, we've had these 2.5-inch drive slots, that have had 10,000 RPM, 15,000 RPM drives for very high performance. But as we saw Flash come on board and have this new opportunity for us, we had platforms that these would easily fit in. So you would see Flash devices with SAS or SATA interfaces that would go into the same servers, the same storage boxes, and would let you mix, some number of rotational devices and some amount of Flash. So it's very simple, very easy to adopt, and it's very scalable. And then as time went on with the 8639 connector, now we could have backplanes we could put NVMe or PCI Express attached SSDs onto. So then we started thinking about, well, what's next? How do we continue this evolution instead of simply taking the slot that we had for magnetic storage for decades? How do we optimize it for our Flash storage? And with that, we have a couple things you have to have. We need hot pluggable devices. They need to be thermally optimized, so something that's not blocking all the airflow going into the box and also not cooking the Flash that's inside of it. And then the two most popular form factors for servers and storage devices are going to be in the 1U and 2U space. So a form factor needs to either be optimal for both, or you split the market and you have an optimized form factor for each one. And finally, you have two different markets. One of these markets is very focused on performance. How many IOPS, how much bandwidth can I get out of an SSD? And then the other side of this is going to be how much NAND can I get inside of a single device? And that's where we've heard about QLC and maybe 5-level cells in the future, but just very bulk Flash, which will start displacing a little more of the hard drive market. So the way we see this playing out is that today's most popular form factor is U.2 by a large margin, and then we have M.2 that's used in the hyperscale and in some mobile applications. But in the future, we expect that to go into 3 different buckets. So when E3 is available in a few years, we expect that that's going to displace a lot of the U.2 market, and it's really optimized for 2U platforms. The E1.L is here and now. There are multiple vendors supporting this, and this is if you really want high capacity, high density in a 1U optimized platform. And then we have M.2. This is traditionally the lower capacities, the 1, 2, and 4 terabytes. But where does that go in the future? And that's where we actually see the E1.S form factor making a lot of sense. That you can have options that are nearly as small and dense as the M.2, and then you have options with integrated heat sinks that allow us to use it in a better manner, gives us the hot pluggability and everything else that we're looking for as we go to scale. So let's talk about E1.S first. There are 5 different thicknesses if you look in the TA1006 specification. However, as I mentioned before, we expect the market to drive 2 separate use cases. One is where you need the smallest device to act as a boot device, something that will be maybe buried inside of a system or simply not taking a lot of space. And on the other side, you can have data drives. This is where you need some sort of performance. Maybe it's high capacity or maybe it's high performance, but they're going to look for larger devices and a lot better throughput. And this is where we see you're going to look at the 9.5, the 15, the 25 millimeter options out there. So in the spec, the 5.9 looks great for the boot drive, and then the 3 asymmetric cases, or the 9.5, the symmetric case, this will give you the thermal capabilities that you need to build an actual system. And for Microsoft, we believe the 15 millimeters is a sweet spot for us, and I'll explain a little more of that later. But regardless of which thickness you pick, what's interesting here is they all use the same PCB. The only difference in these thicknesses is what thermal capability you need out of the device. So about a year ago, we started bringing this challenge up to the industry. We were looking at the 9.5 and the 25 millimeter, and we just didn't see the right fit for our use case in Azure. The 9.5 was very dense, which was excellent, and it was better thermally than an M.2, but it really didn't scale to match our really high performance use cases. And on the flip side, there was the 25 millimeter heatsink option, which was great for thermal, but it didn't allow us to get the density that we're looking for. So what we did, we actually presented to the OCP workgroup this challenge and the thermal methodology and how we might come up with a new form factor. And you can see in this chart here, we looked at many different form factors from 9.5 to 11.5 to 12 to 14 to 15 millimeters. And we tried to look at the trade-offs on how much performance, which you can measure in energy density, and then how much thermal capabilities you can get out of each device. And for us, as you can see highlighted in red, we thought the 15 millimeter was the best compromise. We brought it to OCP and we helped drive this into the E1.S standard. So taking a step back and looking at why 15, why not 9.5 and 25? So I already talked about the performance, but then there's just, how much can you fit in a server? So here's an example of a Project Olympus server that we showed at OCP earlier this year. And our options were we could either put 4 E1.S 15 millimeter, which gave us the performance we needed out of the device, or we could put 2 U.2s in that same space. Well, obviously having 4 flash controllers versus 2 is going to give us the higher performance. So ultimately this makes a lot more sense for us, and we're very excited to see front accessible, high density, and moderately good thermal performance with a 15 millimeter. We expect that's going to give us several generations of devices. So if we look at the 15 millimeter, just like the 9.5s and the 25s, it's very easy to put a latch on this to make it front serviceable. And the exciting part is we're expecting all suppliers are going to be looking at this 15 millimeter and supporting this in the industry. We're already seeing multiple options this year, and by the end of next year we expect all vendors are going to have E1.S 15 millimeter drives available. And again, if someone's application requires a 9.5 and a 25, very likely most providers will include both options. But what about if you need an EDSF device that's actually the highest capacity? Well, E1.S is really tailored to performance. E1L is really the capacity leader. These drives already are at 16 and 32 terabytes today, and you can imagine 64 and 128 in the coming years. So in today's solution, inside of 1U, hot pluggable from the front, you can put half a petabyte in a single box. And in a year or so, we're going to see 1 petabyte in a single U. So if you really need the highest density in the front, easily accessible with good thermal management, the E1.L provides an excellent solution today. And then to pull it back even further, again, this is a family of devices. So if you need high capacity and you really want to get the most in a box, you have the E1.L here today, and you also have the U.2, which will be replaced by E.3 in the coming years. But right now, you also have E1.S, something if you really need U.2-like performance and some thermal capabilities, you can already get that in EDSFF form factor. And what's exciting is they use the same connector, they use a nearly similar latch design, so if you designed one with some minor tweaks, you can put it on either carrier. And both of these can handle 25 plus watts in power, and on some of the E1.Ls go even higher. So if you need this performance and you're not really sure what you need for your device, you can make late binding decisions and actually support both of these technologies. And that's it. Thank you.
So yeah, Jason, there's one question here in the chat that's pretty good. It says, the spec suggests that E1.S could support a max of 25 watts for the 25 millimeter asymmetric heat sink. What are the airflow assumptions for this estimate? And are there any thermal models or test guidance available for EDSFF form factors?
That's actually an excellent question. So in our use case, even with the 15 millimeter, we believe we can cool up to 30 watts on a drive, and every platform is going to be different. So what we've actually kicked off in the OCP work group was a thermal modeling scenario, just how do you model a chassis? And I believe both Microsoft has shared curves, WD and Intel have shared curves, Ross has shared curves on their platforms, and you might be able to look at those and see how does your platform work from an air impedance perspective, and how does that match to the power capabilities you need out of an SSD device. And so what we'll see come out of the OCP work group is hopefully we can find a nice simple way to show that and have multiple vendors collaborate and share what their curves on their devices look like. So it will depend on your platform, but we believe that through some of these modeling efforts we'll be able to help everyone else in the industry benefit from all of our simulation work.
Yeah, thanks, Jason. That was great. Yeah, I think, and to highlight some of the things that Jason said, right? If many vendors can do, similar performance of U.2 in a, we'll say 2, 4, and 8 terabyte range for an E1.S, but it's a smaller form factor and you have more scalability in a one-use server, you're basically getting the same performance in a smaller area at a similar power envelope with, less, thermal requirements. So it's a huge win for the server and platform level design. And with that, I'm going to hand it over to Ross to talk about E1.S at Facebook.
Thank you, John, Michael, and Jason. Appreciate all your insights into this. So let's start off with talking about where we've been before we talk about where we're headed. So let's talk about some of the problems with M.2s today. So power and thermal doesn't scale, and that leads to we're unable to activate the dies and performance limited. This is why M.2s did not scale well past 2 terabytes due to the power and thermal limitations in the data center. There's no standard thermal solution, there's poor serviceability, no hot plug, And so with these challenges, then the question is, where are we headed? So let's talk about some of the benefits of E1S. E1S is a family of a family here where you start with the picture on the right. If you see there's a PCB with an ASIC NAND and firmware, and a variety of thermal solutions where you have a range from high density options to high performance options. Supports hot plug. It works for both storage and compute in 1OU. Supports Gen 4 and Gen 5 PCIe, and it's fully standardized in SNIA. And with that, I think we need to understand this better and talk about what are some background things. So what are the hyperscale needs? The first is IOPS per terabyte need to scale linearly. You see a table here, and as the capacity scales up, the performance also needs. So if you're at 1 terabyte, you have 1x performance. If you're at 4 terabytes, you have 4x performance, and so forth. Low airflow is also critical to ensure there's enough air in the data center to cool. The Facebook data center is 0.145 CFM per watt, and that's very critical to meet. And serviceability matters. It takes a lot of work to keep your data center going, and it's really important to make that as easy as possible. And solutions need to scale for the future. In addition to that, let's look at some of the industry trends here to understand this better. A few things are going on. The first is the 256 gigabit and the 512 gigabit NAND dies are going away. What this results in is the 1 and 2 terabyte data center performance grade SSDs will go away when these dies go away. Dark flash is also becoming a larger issue, where there's flash that cannot be utilized due to changing compute and flash ratios. And Gen 4 and Gen 5 PCIe are coming, which increase power. So now, if we look at this, let's look at some of the trends here on the chart on the left here. You see from 1 to 8 terabytes and 16 terabytes TLC drives, and you see the device power is going up. However, this is not all bad news. If you look at the watts per terabyte, as you can see, when you go to higher capacities, the drives are actually becoming more efficient. What this means is, in the future, the data center SSD capacities are going to increase. Device power budgets will increase. However, the watts per terabyte ratio will decrease, improving power efficiency, which is great news. So what does this mean for us? Here you see a picture of Yosemite V3. If I start at the left here, you see a 25 millimeter E1S latch. This is and you see a 1OU blade, and then you see a chassis, a 4OU chassis, and you see the 1OU blades. If you look at the right, you'll see the chassis with 2OU blades. If we look at these different platforms, they provide different use cases and meet different needs. You'll see how one has 4 SSDs per blade, the other has 6, and the number of SSDs per chassis, one's 48 versus 36, and the maximum blades TLC for the direct connect is 64 terabytes. And for the other platform is 96 terabytes. What this means is that you can have a lot more flash behind a single processor for the platform on the right. And if you also look at the capacity points here, you can see how both platforms are extremely dense and can have very large capacities associated with them. And so one works very well for high performance direct attack storage, and the other works very well for high capacity disaggregated storage. Either way, they scale very well for the future. Now, we've talked about a lot of trends, and we've talked about scaling for the future. Let's see how this all lines up. So if we look at the picture here, you see on the bottom, you see the width needed for E1S to cool based on the CFM per watt. And on the vertical axis, you see the power. The black line here is the CFM per watt of what the platform needs to meet the Facebook CFM per watt requirements. Then we talked about the power for the different capacities from 1 to 16 terabytes and storage class memories. You see where these powers line up. And you also see this gray line here. This shows where M.2 was. So if I start with the M.2, whether you run your M.2s at 8.25 watts or 12 watts, what you can see is when you hit 4 terabytes, the drives are very throttled and you're unable to cool them. This is why 4 terabytes did not do well with M.2s in the data center. But what you can see here is with the 25 millimeter E1S, how the YV3 platform is able to scale all the way to 25 watts and 16 terabyte drives. Thus, the 25 millimeter E1S will scale to meet the power and performance requirements and the low airflow. And this also means that we can scale well for the future. So, thus in closing here, E1S is the form factor for the future. It has great power and performance. It has a standard thermal solution. It's serviceable. It's optimized for the mainstream. And it's very dense. You can fit very large capacities in 1 OU. And so with that, the 25 millimeter E1S scales great for the next generation of storage. So with that, I'd like to say thank you very much for your time, and our data center really appreciates this. And let me hand things off here to John Michael and Jonathan Hinkle here.
All right, thanks guys. So yeah, Ross, Jason, thank you guys so much for giving us the overview of E1.S at Facebook and Microsoft, and Jason, what's going on with the rest of OCP. And Jonathan's going to walk us through what's going on at Lenovo as far as EDSFF. So Jonathan, take it away.
Yeah, thank you, John Michael. So yeah, I think this has been really great. So far you've heard about especially hyperscale use from Jason and Ross. And so I'm going to try to give you a little bit additional perspective because we care obviously about hyperscale and also about enterprise and edge kind of applications for EDSFF. So with E1.S, the vision that that was created around was really a smaller, high density that's optimized for high density form factor that's optimized for the data center. So a new type of SSD, because we don't have to do the same thing with flash as what we've had with hard disk drives. And so just a few of those parameters, and I think some of this has been touched on, but especially I want to sort of point out the system side benefits. We have, again, hot plug and the enterprise feature set that we can support in E1.S. Also, we chose 12 volts as the main power, which allows for the system to be simplified. We don't have to have voltage regulators that add cost and complexity. Whether or not you have the SSDs there, they're all integrated into the device. The LEDs are now on the drive, and really it just gives us that full flexibility of scaling where we don't have to burden the system costs to scale the SSD, number of SSDs we want in the system. And also each of these devices, again, is high performance and capacity. So E1.S, today what you can get, E1.S, you can get 12 terabytes, up to 12 terabytes. There's 4 terabytes and 8 terabytes. And some suppliers with 12 terabytes today, which makes it extremely high density for most, more than the 80 to 20, it's more like the 90-10 or maybe 95% of the market needs can be met with E1.S for capacity per drive. And also you can saturate the PCIe by 4. So if it's a Gen 3, Gen 4, basically the by 4 gigabytes per second bandwidth can be saturated. And we also, as you've seen with John Michael's timeline, we've added by 8 support as well. So it allows for the maximum amount of that flash performance to be captured, and allows for you're not wasting of your dollars that you paid for the flash media. You're getting all the performance out of that. So again, it's designed really with the data center system and also edge systems in mind to scale as mainstream storage. You can scale as you go, add capacity and add performance. It's performance-centric, but also small and modular where you can use it in edge systems. So I think this is something that you've seen a few times now with the different sizes of E1.S, but I wanted to go into a little bit of detail about how this works, because it can be a little confusing if you just look at it for the first time. There are 5 different variants in the spec, but the 5.9 millimeter is different from the other 3 that are really mainstream use. The 5.9 is actually a card definition. So the idea behind this is all done intentionally as far as defining a single card for an NVMe drive that then can be produced and mass-produced by all the SSD suppliers. So there don't have to be different design points for each different type of mechanical. So that just gives you the economies of scale, allows this to be a mass commodity kind of part that's being produced by flash suppliers. But once you have that SSD, that NVMe drive card, then you choose your own standard enclosure, which is the 9.5, 15, or 25 millimeter, or you can have your own custom mechanical. So the 5.9 by itself, if you didn't want to put any type of heat sinking on it beyond that, we're confident that 12 watts from the thermal simulation with a pitch of about 9 millimeters, you can certainly cool that or a little more. But then, typically you're going to put some kind of enclosure on that or some type of rail system, some kind of mechanical, and that's where you get to these standard enclosures. So once you have that base card, then you can go to an enclosure that meets your thermal needs. And so you see the 9.5, when you really have density, that's where you go to the 9.5, where you want to put a large number of devices. And then for something that you want higher power, maybe up to 25 watts or more, but you can still fit, like in O2, you can fit 24 2.5-inch drives today, U.2. With the E1.S 15 millimeter, you can still fit 24. So maybe with the 9.5, you can fit 32. With the 15 millimeter, you can fit around 24. So it's like what you used to be able to only do in a 2U, now you can do that in a 1U. And then for when you really need the thermal headroom, especially when you're trying to run lower airflow to help with your overall TCO in a very, very large data center at hyperscale like Facebook, or if you want to go to the highest power over 25 watts plus, then that's where you go to 25 millimeter. So you can see some of these thermal characteristics, some of the testing that's already been done in simulation. I think there are some specs. I think there was a question earlier. There are some specs that were referring to thermals. I think there are some already in the EDSFF specs in SSFF on the SNIA website. So there are some thermal aspects of this already published in the specs, and also OCP has been contributing to that. Okay, so for the use cases and systems, again, just wanted to sort of highlight where those different use cases hit, especially for it could be hyperscale or it could be enterprise. But then for smaller footprint, for edge servers, for blade servers, for dense systems that are scaled, multi-node in the system, then that's where E1.S can really shine for putting a large number of devices where you only had room for maybe 2 U.2s or 2.5-inch drives. So now you can get a lot more performance and more capacity as well, and do new things with the smaller systems. And then also for 1U servers, when you want to scale that performance into a little bit larger form factor, the 1U is obviously optimized for that 1U. Again, with that horizontal backplane with the right angle orthogonal EDSFF connector, then you can get the best thermals and scale your capacity and your performance. You can get at least 16 up to maybe even 32 E1.S's in a 1U. The benefit there is, really that's the most capacity that most customers will need, especially in the enterprise. And most customers don't spend more than $100,000 worth of flash in a single system. So capacity-wise, you've really hit the maximum need of the industry, but you get all the performance out of all that flash with simple scaling of by-4s. Then 2U on larger systems, if you really want the highest performance, also if you're doing dual port, if you have a by-4, you can do 2x2. Or if you're doing a by 8, you could do 4x4. I'm sorry, 2x4, or 4x2. So basically 2x4s. So dual ported is supported in the EDSFF connector and all the form factors. And then that's really something where you're again looking for U.2 replacement. One of the alternatives we think at Lenovo that may be used there as well, especially, is E3.S. So we see one variant of E3, especially the thick E3.S, is really interesting for the highest capacity. Where you want to scale capacity beyond the performance you need in a by-4, then that's very useful. Again, by-4 slots commonly are really ideal because we don't have the stranded lanes, and there's no customer limitations as far as which slots you can plug into versus others. Also, the power per device in front of the processor of the server, we really want to keep that at a reasonable level. So 25 watts is the limit. Larger number of devices, say 24 to 32, we really don't want to scale too much past that, except in certain niche cases, because of the power in front of the processor. You want to still be able to cool the processor and everything else in the server. So again, I think these are some of the same system benefits you've seen in some of the other slides. Again, smaller allows for that higher density. The thermal solution is much better, especially with the horizontal backplane, but overall with a smaller form factor and then more open space just from being smaller. Also, the overall infrastructure costs can go down. These are less expensive card edge connectors. And so ideal cases for E1 to S include all the different form factor of types of servers as well as edge servers. You're either scaling up in larger systems or in edge systems you can get more capability that you couldn't have before. And especially I think the focus for E1 to S, 6 to 25 watts, allows for this sort of balance of power and cooling while you're still getting the max performance out of the link. Also E1 to S is definitely coming, DRAM memory, persistent memory. There's new interfaces, C6, CXL, that are going to allow us to have low latency attached to E1 to S, computational storage and acceleration. So there's a lot of different use cases where E1 to S, you'll see it broadening out over time. Okay, and that's all I have here. So thank you, and turn it over to Paul and Bill.
Thank you much. I appreciate that. So my name is Bill Lynn. I'm in the Server Advanced Engineering group at Dell. I'm responsible for PowerEdge storage architecture. So today, along with Paul Kaler from HPE, we're going to talk about the E3 form factor and what's going on in that space. So basically, E3 is a family of form factors. It includes currently 4 different device types that we call the E3S, the E3S 2X, which is the E3 short thick. We have an E3 long, and then we have an E3 long 2X or E3 long thick. These are, all of these are 76 millimeters tall. The short versions are 112.75 millimeters. The long versions are 142.2 millimeters. So you can think of these, roughly as the short ones are the length of a 2.5-inch drive, and the long ones are roughly the length of a 3.5-inch drive. So they're roughly equivalent volumetrically. So a couple of things have changed in the E3 space. An E3 is defined in SFF-TA-1008. That's the SFF spec that covers the E3 form factor. A version 1 was put out probably about 5-6 months ago at least. There were some changes that we decided to go do within that. We reopened up that specification. We are working on a version 2 now. And essentially the big things that we're changing in version 2 is we made the E3 short a little bit longer. It was 104 millimeters. We increased the length to 112.75. And that's so that we can hopefully leverage an E3 or an E1S PCB inside of an E3 case, and Paul's going to talk about that a little later. The other thing we did was we've moved the connector registration point up about, I think it was 19 millimeters, so that it's not down at the bottom of the form factor, it's more towards center. One, that helps us with our E1 PCB leverage story, but it also allows us to have a power tab under that allows us to go to a lot higher powers. So right now the goal is for the E1S, or E3S, I'm sorry, I keep calling it E1, E3S, the E3 short, to be around 20 to 25 watts. The E3 short thick to be around 35 to 40 watts, and then the E3 long will be up to 40 watts, and then the E3 long thick, or 2X, will be up to about 70 watts. And the reason we want to do this is we're targeting more than just SSDs. There are many other device types that we want to target with this form factor. So when we went back and looked at what are the industry architectural requirements, we want to define a family of devices that will last more than 10 years. And if you go back and look at the 2.5-inch drive form factor, it's been around probably close to 25 years. So that form factor has really, done very, very well in the industry, and we're hoping that E3 will have a similar lifetime. So to do that, there are a couple of things you really need to do. One is the common connector definition. That's based off of SFF-TA-1002. So with that connector, we can support multiple protocols. We can support generic PCIe, we can support NVMe, we can support CXL and Gen Z. The form factor is also big enough, given that it's 76 millimeters tall, that we can support different link widths going back to the host. So we can support a by 4, which will probably be the standard for SSDs. But we can also support by 8 and even by 16 if we want to. The other thing that we believe TA-1002 will give us is support for multiple PCIe generations. It's a very, very high performance connector, so we are hoping that it will support us at least through PCIe Gen 6 and maybe Gen 7, if anybody ever figures out what that is. Like I said, we picked a 76 millimeter because it enables a bunch of different multiple use cases, and it fits into our classical chassis constraints. So the E3 works in both 1U and 2U chassis, and we'll have some pictures a little bit later that shows how that works. It's optimized to maximize the capacity, but also it doesn't break our traditional chassis depth constraints. So we can't build chassis that are so deep that they blow out the back of the racks. The device thicknesses, those allow us to maximize capacity, but it also allows us to put other types of devices that may require much higher power. And that's mainly around GPUs, accelerators of different types, and storage class memory that's coming with CXL. So, and like I said, you need a common connector registration point. So this allows us, since the connector is in the same place on all 4 variants, it allows us to take a short device and plug it into a longer slot. It allows a thick device to work in 2 thin slots, and it allows smaller devices to work inside larger envelopes. So it's kind of like a Russian doll type thing where you can put smaller things in larger elements. Like I said, it's a cohesive family of devices. The E3 Long 2X, we're targeting for 70 watt. We're looking at that for higher end accelerators, computational storage, and also another thing that we're looking at is using this device for front I/O. So one thing that Paul will show a little bit later in the presentation, if you take the E3 Long 2X thick form factor and overlay it on top of an OCP3 NIC, it actually fits. And that's one of the things is we made sure that the connector registration point lines up with a 4C plus connector that's used on OCP3 NIC. And with the thick form factor, you can actually fit the networking connectors coming out the front. I think several people have mentioned before, but the E3 short, we're targeting from 20 to 25 watts. That, we believe, is going to be the mainstream replacement for the U.2 drives that are shipping today. The E3 short 2X, that's another one that can be used for either accelerators, for very high capacity SSDs. It can be used for front I/O again, for NICs. So it's got a plethora of use cases that we're targeting. Like I said, it's an interoperable family of devices. So the whole goal of it is if you have a system that has, let's say, 40 to 46 slots in the front of it, you can fill that up with a bunch of E3 short thins, or you can, have some of them be E3 short thins. You can plug in an E3 short thick into 2 E3 short thin slots. If you have a deep enough chassis, you can have that backplane pushed back slightly, and you can fit the E3 longs in there, or you can take an E3 short and plug it into that E3 long slot. You'll have to have a different carrier, and you'll have to light pipe the LEDs up to the front, but it's just a small insert that goes in there. So that allows you a lot of flexibility of, let's say you want to build a server that's absolutely maximized for capacity, so you build it all with E3 longs, but let's say you're starting out with smaller capacities. It allows us to offer capacity points in one form factor that will work across the spectrum of slots. So let's see, going next. Actually, as we get into form factor design advantages, I'm going to hand this over to Paul Kaler and let him talk about some of the advantages he sees for E3. Paul?
Thanks, Bill. Yeah, so now that Bill's got everybody up to speed on E3 and all the 4 variants of E3 and all their dimensions and capabilities, we've got everybody who's an expert now on E3. That's great. Let's talk about some of the design advantages. So, something that Bill touched on is supporting a wide range of power profiles, and so that's something that's really important because we have a lot of device types that we want to be able to support, so the E3 family provides that. The current EDSFF pinout that everyone's mentioned for the standard connector that we use, the SFF TA1002, that connector base supports almost 80 watts of maximum power delivery. So again, we've got lots of room to grow, lots of headroom on that connector. And of course, those higher power capabilities allow for much more powerful device types. So when we're talking about especially things beyond NVMe, like accelerators and other device types, those are the device types that we really see as kind of like future devices, but being able to take advantage of these. So it's kind of a good future-proofing capability. But even if we just look at NVMe devices, E3 is also going to be able to support some of the higher power profiles that we see are going to be needed for NVMe. As we're looking at PCIe Gen 5 and be able to saturate a PCIe Gen 5 by 4 link, those power profiles are going to be pretty high in the 35, 40 watt range. And so especially as we talk about being able to support PCIe Gen 5 and beyond, we start to see that the E3 thick will actually be a very good vehicle for that. The E3 2X, again, that 2X is the designator for the thickness. And so we see that form factor would be very well suited to be able to support the very high performance end of the NVMe market. And we did, I think someone mentioned this earlier, there's been a lot of work done in OCP about kind of doing thermal methodologies and how to figure out, what can be cooled. We've actually opened up a spec as really kind of taking some of the thermals that were in the original E3 spec, and we've decided to move that into a more fully based thermal specification. And so in SNIA, we've opened up a new spec called SFF TA1023, which is a thermal specification for EDSFF devices. And in there, we're going to define some of the characteristics that are needed to be able to characterize these devices, determine, based on different designs, what their impedance is and what their maximum temperature and airflow would be to be able to be cooled in a device. And that'll give us better feedback, too, on what types of power profiles we can support. There is ongoing work there, too, within OCP to provide feedback in, and then the standard will be created in SFF under that 1023 spec. And then on the wide range of device types that are supported as well, as Bill mentioned, the ability to support multiple PCIe lanes in the device in the form of a by4, a by8, or a by16 interface that allows a huge range of device types, from a standard mainstream NVMe that's probably going to use a by4 And if that's an enterprise storage use case, it might be a dual-ported 2x2 interface. And then if you wanted to have even higher performance in a dual port, you could go to the by 8 or the by 16, supporting a 2x4 or a 2x8. So that gives you lots of flexibility on how you want to configure your systems in dual port modes. Plus, with different device types, you've now got CXL where you may have DRAM attached. And so in those interfaces, you may want to support a by 16 interface to get the full kind of DDR type bandwidth needed to the device in a CXL architecture. And then if we look at the device thicknesses, like for a thick, a 2X device, Bill mentioned this actually earlier, so it allows, there's enough room on the faceplate now in the front of the case to be able to support standard networking connectors. So if we want to look at some different network device types, now you've got the front space available to support that. And then, of course, this one's kind of obvious, but sometimes it just needs to be mentioned. The larger PCB surface, being this is a 76 millimeter tall device, obviously it allows for NAND package placement, so you can support really large capacity points. And then in addition to that, you can have a support for richer device types and that might need really large ASICs. So some of these computational storage devices we might see in the future, or accelerators where they might have an FPGA or a really large ASIC, the larger PCB surface, of course, enables a lot of those types of device types as well. Then if we look at kind of touching on the interoperability of the form factors, as Bill mentioned, the 1X, the thin and the thick, the 1X and 2X devices are interchangeable. So what's really great about that is you don't have to have a custom chassis, which is a big deal, right? So you can share chassis designs, share mechanicals. Your drive cages don't have to be customized for one of the form factors. It can be the same mechanicals, and through a carrier you can support doing the interoperability of saying in one thick slot you could pull that one thick device out and you could put in two thin devices in that same slot, and all the mechanicals are interchangeable that way. So that's great for our chassis and lowering cost and solution cost to customers. So that's really a great benefit there. And then, of course, being able to balance the device size and the different device types to the infrastructure requirements. So if you've got a certain number of PCIe lanes available on your server and you're trying to map that and you want to have the right number of devices, and the device sizes can complement that, so you can mix and match thins and thicks depending on what type of device you're using. So you might have some 1X thin devices mixed in with some 2X, and we'll get to some of that in some pictures and kind of show what the modularity can enable. And then, as I mentioned earlier on the power profiles, this is, of course, having those interoperable device form factors allows you to right-size the power profiles to your bandwidth capabilities or what you're trying to drive in and out of the system. So that right-sizing is great with being able to switch out the form factors to what power capabilities you need to drive the bandwidth you need. And then this one, the last one here, is a really important one from our customers that's driven pretty hard, right? So you can imagine we sell lots of 1U and 2U server chassis. If you're a customer, you've got a lot of these in your data center, and this has been a big one where they say, we don't want to have separate drives in our 1U servers and our 2U servers. We want to have a common pool of spares, and so we want all the different server types that we buy from you, we want to have one device type. And the 2.5 inch has been really great in that case, because that's what we've had predominantly now for, as Bill mentioned, over 20 years. That has been a prevalent form factor, so that's kind of what everybody's used to. So we're trying to kind of accommodate that well moving forward so that our 1U and 2U chassis can still take advantage of a shared form factor. So now let me show a couple of just, these are not product kind of decision points or showing future products necessarily. This is just to kind of look at what some of the different configurations can be between the 1U and the 2U servers. So you can kind of see how we can leverage the same form factor between the two server chassis units. So clearly on the top here, that's a very storage dense configuration, right? You would have support for maximum number of drives with 20 E3 1X storage devices. Then in the middle, you might have a scenario where you've got some very high power CPUs or maybe even a GPU in the back, and you want to have a lot more airflow to cool those devices. So you might have a less dense front end, so you could have a big airflow channel to provide lots of cooling to your downstream components. And then you see another configuration where we talked about the kind of mixing between thins and thicks, the 1X and 2X devices, where you can have some mainstream NVMe drives mixed in with some storage class memory and maybe some accelerators. Moving forward to the 2U, you can kind of see it's really kind of the same principle, just in the 2U chassis, where you'd see on the top here, you can see a very dense storage configuration where you may not have that many downstream components that need high performance or power. And so you can really kind of take advantage of all the volumetric to really have a very dense storage configuration. And then on the bottom, same type of, where you might have a mix of mainstream NVMe drives up to 20 or 25 watts, mixed in with some storage class memory and accelerators with, potentially some airflow channels that help the cooling in the back. And of course, you can mix and match these around so they don't have to be, this is just one configuration to show what it would look like, but clearly you could have a mix of storage class memory or accelerators next to each other, or you could put them in different locations of the server, but all this is just to show some optional configuration options. So now to get to some of the new things that are happening in the version 2 spec that Bill alluded to. So this kind of gives you a cutaway view of some of the changes that we made and why we made them. And so this is really about the connector registration change that Bill mentioned of the 19.5 millimeter change now. And so what we looked at was, for E3, there is certainly a range of capacities needed for these drives. And so on the lower end, where the smaller capacities are needed, it makes a ton of sense to leverage the family of EDSFF. And so we looked at it and saying, well, if we could use an actual E1S 5.9 millimeter base PCBA design, like several folks have mentioned, leveraging that across the volumes is a great way to do it. I said, well, we can also use that in an E1S, in an E3 case, and that way we can drive all of the volumes for those lower capacity points in E3. We can add those to the volumes of E1S, and so that's really great because that combines all those volumes and lowers costs for everybody. And so we made some changes. We lengthened the case, like Bill mentioned, to be able to accommodate the longer E1S, and we also then pick up some by raising the connector registration up. You can still see by the blue kind of pin tab locations that it still supports a by 8 and a by 16 with this increase, but it allows us to pick up some of the LED locations natively on an E1S. And it also clears some mechanical interferences along the bottom of the chassis so that way we have a very easy way to implement E1S into an E3 case. And then this is the other reason why we moved that connector up 19.54 millimeters. You can see here the OCP NIC picture here on the right uses a variant of that same SFF TA1002 connector. They use the 4C plus version of that connector, and that has this extra tab here down on the bottom for a bunch of additional sidebands. And so by moving our connector up, we free up this space down here, and that allows us to be able to use a 4C plus connector. So you can see here from the overlay that a OCP NIC 3.0 design is almost identical to the E3 form factor. So it'd be very easy to leverage an OCP NIC design into an E3 form factor. And now that the connector registration is moved, that would also support that use case. So it'd be extremely easy for a NIC vendor to come along and say, hey, if I want to add some more NIC devices on the front of a server, I could go design this into an E3 case, and then we'd have front accessible NICs. And like Bill mentioned as well, we have a thicker case design which can support kind of the industry standard NIC interfaces. And this creating this space at the bottom enables us to support higher power devices because there is another variant of this connector, the 4C high power connector, that has a tab that supports a huge amount of additional power. We don't need that much additional power, but in the future, if certain device types came along and they said, wow, we really wish there was some more power available beyond that 80 watts that this connector natively supports, we could actually support developing a new connector and adding in a tab right there that basically supports we could call it a medium power connector that could add potentially 200 watts of available power to this form factor. And that might wind up creating a new device type where they might say, well, we want to go to a 3x or a 4x thickness for a GPU use case. So this is all about trying to future-proof the form factors and trying to create room to grow so that we could really leverage this and hopefully have a lifespan as long as we had in the 2.5-inch world. So with that, I think that is the end of our presentation. So thanks to everybody for listening in, and I'll move this on next to John.
Yeah, thanks. Thank you, Bill, and thank you, Paul. That was awesome. I think now if anybody asks me about E3, I can send them this webcast. Before we go to you, there's a few pretty basic questions that people ask in the audience. And thank you, guys. Keep asking questions. Sorry if we can't get them right away. And by the way, if we don't get to them all today on the webcast, we'll open up a SNIA Q&A on the SNIA website where we can answer the questions. There's a couple basic questions. One about does EDSFF support hot plug? Yes, all the form factors natively support hot plug, and the connector has been designed to support hot plug. And then, does EDSFF support NVMe? It sure does, right? Runs PCI Express is the current pinout specification in SFF TA 1009, which defines how to use a PCIe SSD, and then NVMe Express runs on top of the PCIe. And then in that, there's also a question about, does this connector and form factor support dual port or high availability storage? And the answer is yes. In the TA 1009 spec, there is a dual port enable pin, and it's an active low signal, and if that signal, it indicates that the dual port mode is supported by the host, so the SSD can go into a 2x2 mode or whatnot. So the other one, I'm going to let John, there's a question here if you want to answer it. To say if the 1 in E1.L means and E1.S means one rack unit, what does the 3 in E3 family mean? Does that mean it's compatible with 1U and 2U?
No, we were our usual consistent self. And hello, everyone. I'm John Geldman from Kioxia. We were our usual consistent selves. The 1 in E1 means that it does in fact work in a 1U rack, and it is designed and optimized for that. And the 3 in E3 means that it's 3 inches. And there's the secret decoder ring.
You got it. Yeah, so I think if you heard John, E1 is definitely optimized for 1U form factor. E3, you guys saw examples of where one can be used in either or, right? Where E3 is 2U optimized, but can be fit horizontally in a 1U to have a common drive type between 1U and 2U. But in hyperscale systems where the mainstream unit of scaling is a 1U form factor, right? That's really where the E1.S and E1.L shine, and that's where you've heard a lot from Jason and Ross on that topic. And then the other question I think I'll ask, I'll try to answer more of these at the end here when we have time, but can a 2U system plug in 2 E1.S into the same bay as a 1 E3.S?
You want me to take that?
Yeah, sure. A few ways we can answer that, but yeah, Paul, why don't you take it?
Yeah, so I think, right, mechanically you can make almost anything work. So I think it's just a question of whether that makes sense from a scalability and cost-effective. Right, if you're adding in more sheet metal to be able to take multiple E1Ss into the same bay, that then becomes maybe not the most cost-effective way to scale capacity. So I think absolutely it's feasible mechanically and can be done. It just comes down to, I think, a business case of whether that makes sense.
Actually, there's going to be a problem because the connector registration is different between the two. So the connectors aren't going to line up.
Yeah, it would definitely require, right, I think it would require a custom backplane. So it just depends, I guess, on if the question is whether it's, just into the mechanical bay can you fit to versus whether you can really fit to in an interchangeable manner. And I think there's certainly a different answer for those two.
Right, there's some concept designs where there's a GU chassis where there's 2 rows of E1.S, and that's kind of doing the same thing, like you mentioned, where mechanically you can fit 2 E1.S in the same similar dimensions. But there are some ways that Paul talked about, like where we're looking at E1.S interoperability in an E3 enclosure or carrier for chassis that already accept an E3 backplane. All right, so thanks, guys. We'll answer the rest of the questions towards the end. I'm going to let John keep going, and thank you guys for bearing with us on this long webcast, but I think it's really important. We have a lot of awesome topics. So, John, take it away.
All right, thank you. So I work at Kioxia, but I'm also in an awful lot of standards groups, as you may have seen on the bio. And actually, everybody who's been talking so far is very active in the standards group, not just myself. What we really do in the standards group is we start from our, developing our drawings and, well, whatnot, and end up in physical representations. For E3, as has been described, we're actually going back to the drawing boards and improving it in a couple of ways, and you'll get to see another. We really do get to real instantiations, and that's what you're starting to see today in systems starting to get developed. What I want to talk about from a standards developer point of view is something of what's been talked about already and explained from the point of view of every system, but I want to get to a little bit more basics to it. As we move up the technology curve for PCIe for Gen 5 and Gen 6, we really do increase the pure amount of bandwidth, and that has some heat effects. And we also really make signal integrity a lot harder. And as we do that, the 1002 connector, which we took somewhat from Gen Z, is a really good connector for this, making the connector not the problem as we work out our signal integrity issues. So between the NAND advantages that you see with the latest generations of NANDs and the higher bandwidth being made available, we really increase the thermal load. And what we've done when we work on EDSFF is really design with this thermal load in mind. I don't talk a lot about it in these slides. Well, I'll talk a little bit more about it later. Well, we've already talked about in OCP. There's some work going on right now. There has been work going on in thermal. We switched that load over to SFF for them to continue the work, but we're running out of time in those meetings, and we've actually gone back to OCP to do some more development work on the spec, but you'll eventually see it coming out of small form factor. So if you want to come see what's going on, those are the places to be. So the E3 reboot is actually a very positive thing, and one of the key things to note there, and I'll show one quick picture reminder. So in this real instantiation of E3, you'll notice this one happens to have a by 8 configuration, which is kind of works well with this space, increases heat and all that. But the connector has actually shifted. I would have shown another by 8, but the only drawing I had was for a by 4. So we've shifted that up, and what that means is these things are not compatible. And so this guy, even though there's some real ones floating around, you will not see it in real production. So we are seeing that 2.5-inch drives at this point, to answer the question of, that was really the headline of this panel, is it's going to be around for a while. But it's going to be starting to struggle with increases in power requirements, increases in problems with signal integrity. It's going to start to run out of steam as time goes on. Another interesting thing that worked for 2.5-inch devices is you could throw HDDs into those. And as HDDs have to continue to compete with the increasing volumes of SSDs for lower bit cost, the systems may want to focus more on 3.5-inch rather than 2-inch. So a lot of times from my standards world, where I work on almost all the standards used in storage, if not all of the standards used in storage, people ask, who's going to be the winner? Which of these is going to be the most popular? And I think the proper answer is it really is a family affair. And if you don't like your neighbor, you can ask me to sing some Sly and the Family Stone. You don't want that. But it is a family affair. You're seeing that the M.2 use cases, you've seen them migrate well to E1.S. You've seen the 2.5-inch use cases, the way that those were used. That works well with the E3. And the E1L and the E3L are opening up new use cases that were beyond those. The new capacities, the storage class memories, the higher power accelerators, and we're seeing all of that happen. One of the things that makes me happy as a standards guy is when your stuff that you designed for one thing gets used for something else because it's useful. and I think EDSFF is passing that test.
John, let me, for the last
Sure.
second, I don't know if it's going to, Bright Talk might kick us off here in a sec, because I think we had allocated 75 minutes. So if it does do that, then we'll follow up in the blog. Hopefully not. Hopefully it lets us go over. But they used to just shut it down at the end. But yeah, once we end this today, we're probably not going to have a ton of time for questions. So we'll just go ahead and kick off a SNIA blog where we'll go answer the questions. Okay, great. It didn't boot us out. So go ahead, keep going, John.
Okay. All right. Thanks for the warning. So I'm going to jump ahead and try to get through there aren't very many slides left here. So the reboot, as I've already said, it's not compatible. It does a great job of bringing in the OCP NIC functionality, which gives us the power tab has been talked about. It lets us reuse our E1.S PCBs for those of us who are in the business, which is great for those low capacity designs, which is fun to say for our less than 10 terabyte that are on E1S, are low capacities. And by the way, we're also seeing an awful lot of efforts to migrate HDDs into these systems, because we are seeing that EDSFF is sort of taking over, and hard disks want to find ways of remaining relevant and fitting in slots. And so E3 form factors are kind of an obvious solution for 2.5. And there's actually a lot of work going on in standards now in OCP and NVMe. Come join us in those environments also if you are interested to see how HDDs will work in a PCIe NVMe solution. I think we've already heard a lot of this observation of EDSFF interest, and since I seem to be just about out of time, I'm not going to really cover that and see if there's one question. So I think the quick answer on one thing is clients. This is the enterprise and data center small form factor, not the client. And we've got about 2 seconds. That was the quick answer. You may see E1.S coming, but that's about all we've got. Any 1 second words, John Michael?
No, thanks. Yeah, you guys asked a lot of awesome questions. Like I said, unfortunately, we don't have time today because Bright Talk's going to kick us off here. It just gave us a warning in about 1 minute. So we'll kick off a SNIA blog, and I just want to say thank you again to the presenters for doing an awesome job. These guys are the ones doing all the hard work developing the specifications, and we're all working together to get the EDSFF family of form factors off the ground. And really, a lot of people asked a lot of questions about the the volumes and forecasts. And yeah, we're really excited and bullish about EDSFF being really the standard form factor for data center SSDs going forward. So I'll leave it at that, and thank you guys again for joining, and we will come back soon. So, thank you all. Bye-bye.
And I'll echo the thank you.